Okay, so I'm going to do a whole bunch of stuff on RC circuits. It's going to be crazy. I mean, this might take 5 hours. This might be a 5-hour video, but it's not going to be 5 hours. So let's look at this RC circuit, and we're gonna collect data. We're gonna model it. We're gonna use calculus. So let's just get started with a demo right here. I'm gonna do this demo right here. Okay, so a capacitor. I have a capacitor right here, and they turn off this camera so it doesn't bother me. So right here I have a capacitor, and this is a 1 farad capacitor. So if you want to think of this as 2 parallel plates that you can store charge on, I mean, I think I'm cool with that. But let's just do a simple demo first. So I have my capacitor. Actually, I don't even know if that's charged or not. Let me discharge that. So I'm going to take this wire and just discharge it. Okay. So now here I have a light bulb. Let's see if this light bulb lights up. I wanted to just use 1 battery, but I might have to use 2. So I know my wires are a little long. Please forgive me. I'm going to plug in that one. I'm going to take my other wire that I just used right there. And one of the tricks I use, I put these little magnets on the batteries. These neodymium magnets are conducting, so you can just do that. Isn't that cool? Okay. So now if I hook this up, you can't really see that. So let's use 2 batteries. I'm going to take this one. So yeah, I can even do that. What do you think about that? Are you impressed? Okay, that's brighter. Okay, so now what's going to happen if I connect this? And this does have a polarity. I think the double lines mean positive, so I'm going to hook this to the positive side right there. So I'm going to hook this there. Now I'm going to have a battery to the light bulb, to the capacitor, and then back to the battery. So I just need this, and let's watch what happens. And I'm going to connect it. I'm just going to hold it, actually. And you'll notice that the light bulb is getting dimmer and dimmer and dimmer and dimmer. And so that means that the current is decreasing. So eventually we'll get to the point where there's no current flowing. So at that point, if we use the loop rule, and I'm going to draw this in paper, then the voltage around the whole thing has to be 0. So this 3 volts to 1.5 volt batteries would have to be the voltage across this, because if there was a voltage across that light bulb, then there'd be a current through it and it would light up, but it's not lit up. Okay, so now the next thing, I now have that charged, and I can discharge that through the light bulb. And let's watch what happens here. And this is really what we're going to model. So now it starts off bright, and it gets dimmer again. But there's no battery. So I'm discharging the capacitor. It's going through the light bulb until there's essentially no more charge left, and the light bulb goes off. Okay, so this is really the situation we want to look at. Let's start off with that. Let's do the first one first. Actually, let's start with the first. I almost used the wrong pen. Okay, so here is my first RC circuit. I have graph paper over here. We're going to be making a graph later. Okay, so here I have a battery. And then I have a resistor. And then I have a capacitor. When I close the switch, let's say this is EMF. That's what we use EMF for the battery voltage for electromotive force, and this is the positive and the negative end. And then we have conventional current going this way, and that's resistor R. So, and this is my capacitor. Once this current flows, I have charge build up right there, and that pushes charge on that side. This produces an electric field inside going that way. So when I do the loop rule says the change in voltage around any loop is equal to 0. So if I go around this loop that way, I'm going to get EMF, and then I'm going to get the voltage across this is minus IR, and then right here I'm going to get, I'm going in the same direction as the electric field, so I'm going to get minus the voltage across the capacitor. And that has to be equal to 0. Now, the voltage on a capacitor is V capacitor is Q over C. So as the charge on the capacitor increases, the voltage increases. Eventually, this value is the same as that, and that's 0. And that's what happens to the light bulb. It starts off with no charge on the capacitor, so no voltage, so you get a lot of current flowing through the resistor. As this increases, it decreases the current, and the bulb decreases in brightness. Now, the second case is this. So now I have a capacitor, a charged capacitor, and a resistor. In this case, it starts off with positive charge, and then that creates an electric current. That current runs through here. In this case, I get the following equation. Delta V equals 0. So that's going to be equal to Q over C minus I R, where I is the current. And that's going to have to be equal to 0. So let's solve this equation. And I'm going to make a slight mistake, but I'm going to solve this explicitly, and then we can model this on a computer. Okay, so if I want to get this as a differential equation, it's important to know that the current is defined as dq dt. It's the rate that charge flows. Okay, it's the rate of charge in coulombs per second, and that is an amp. So I can put that in right up here, but I'm going to have to put in I have a problem, right? Because this is the charge on the capacitor, and this is the flow of the charge. And so one of those has to be negative, right? Because they're not the same thing. They're not the same Q's. This dq is how much the charge changes, so that's actually negative. So if I put that in up here, I actually get 0 equals Q over C plus dq dt times R, because it's minus a negative. I make this mistake all the time, okay? But there, I've done it. So now I just want to solve this for, let's just put one term on each side. So I'm going to subtract QC from both sides. And I get, I'm going to do this I'm going to solve this equation. This is a differential equation. Okay, let's solve this. So here I have 0 equals Q over C plus dq dt R. So I'm going to subtract that from both sides, and I get dq dt R equals negative Q over C. Now I have two variables. I have the Q variable and I have the T variable. So I can separate these out. So I'm going to multiply both sides by dt over R and divide both sides by Q. And I get dq over Q equals negative dt over RC. Okay, I hope you see how I got that from there. Now I have just Q terms, and R and C are constant. I have just T terms. So I can integrate both sides. I'm going to integrate this from Q0 to some Q prime, let's call it, at some time later, and this from T equals 0 to T prime, right? So if I integrate this, I have dq over Q. I can integrate that. And the answer is the natural log of Q. So this is going to be ln of Q from Q0 to Q prime equals, this side is pretty easy to integrate because I just have a constant RC, so this is going to be equal to negative T over RC from 0 to T prime. So if I evaluate this, I get natural log of Q prime over Q 0 equals negative T prime over RC. Now I can take the exponential of both sides to get rid of the natural log, and I get Q prime over Q0 equals e to the negative T prime over RC. And so this prime stuff, it's just because that's my I can't have the same integration variable as my limits variable. It's bad form. It's rude. That's what it is. It's mathematically rude. Okay, so now I can, I don't want Q, right? And I don't want Q naught, and I don't want Q prime. So if you remember, the voltage across the capacitor is equal to Q over C. So Q is equal to C times V. So if I put in up here, I can get the voltage, the current voltage is a function of time, V as a function of time, is going to be equal to, well, let's see, Q is going to be this time C, but then I'm going to, yeah, let's put it right there, divided by V0 C, that's the same thing, is equal to e to the negative, and I'm going to switch this to match this time. I'm just going to call that time again. And it is a little rude, I admit. It's a little rude. These C's cancel, and I get V as a function of time is V0 e to the negative t over RC. So this says that as t increases, this gets closer and closer to 0. As t increases, yeah, that's right. Okay, I just had to think for a second there. And so this does give the classic discharge current thing. And we're going to use this in a real situation that's online and not real to find the value of a capacitor. Okay, so here's what we're going to do. So here is my capacitor and my resistor. And if I measure, let's say, the voltage across the capacitor with the voltmeter as a function of time, then I should get this. V as a function of time is V0 e to the negative t over RC. And so I should be able to collect data, which I'm actually going to do, V, t, for a certain situation. Let's model that with a Phet simulation. Okay, so I'm going to switch over here to the computer. So this is super awesome. This is Phet, I'll include the link down below, makes brilliant, super awesome simulations. This one has a problem in that it's Java. So it might be difficult for you to run it, and that's when I'm going to run it for you. This is the circuit construction kit with AC and DC, but it has capacitors in there. The other DC construction kit is really good, and it's HTML5, but it does not have a capacitor in there, so you can't really do the same thing. So I've already started off with a battery. This is my, I think it's a 9-volt battery, a resistor, and I'm going to tell you what the resistor is. It is, let's see, I think it's a 100 ohm resistor. And then I don't know the value of the capacitor. So let's hook all these up. And then I want to discharge through the resistor. So let's do it like this. Let's put this here. Let's put this here. Let's put this here. Okay. So I first want to charge this. I'm going to need a switch. Let's put a switch here. And let's put a switch here. So let's connect this. Let's put it like this. Let's make it look nice. Put that there. And let's get some wires. Oops. So here's my wire. Another wire. Put it all pretty looking. That's good. Okay. So there's that. Another wire. Another wire, another wire, and then one more up here. Okay, so there I have the one nice thing, it also shows you this model of where the electrons are and stuff, so you can kind of see what it looks like. So what I'm going to do is close the switch to charge the capacitor, and then I want to connect that switch, that battery, and then discharge through this resistor down here. Now, yeah, that'll work. So I just need another down here. It's fun to build these circuits. And it's really great because you can do this and you don't actually have to have the stuff. Okay, so let's just run this and see how this is going to work. So I'm going to click play. And I'm going to close the switch. And you'll see that this has charge up. You can actually see the charge on there. Now I'm going to disconnect the switch. And I'm going to connect this one. Is it discharging? Okay, it is. So let's see. We can actually measure this voltage with the voltmeter. So let's put my voltmeter right here. Put my plus. And my minus. Yeah, see, it's going down. Okay, so let's just, I want to just charge it back up so that I can get it back the way I had it. So I'm going to press play. Let's open the switch. Close the switch. And so then we can get this all the way up to 9 volts. It doesn't go instantaneously because there is resistance in the wires. Okay, So here's what we're going to do. I want to collect data, and I'm going to write it down. You can write it down too. I'm going to pause this. I'm going to open this. I'm going to pause it. And I'm going to close the switch, and it doesn't run because I paused time. Okay, and I'm going to get my stopwatch out. Stopwatch. Reset. So now I can write down this first voltage. I know the voltage across the capacitor is 9, and the time is 0. Now I'm going to play it and stop it. So let's see, I stopped that. And then we'll record the time again. Now what you would do in a real experiment, you can't pause time. So what you could do is run it for 3 seconds, start over, run it for 4 seconds, start over, run it for 5 seconds, and so forth. But we don't have to do that. So we could get, let's say, 5 or 6 data points here, but who cares? Let's just see how it goes. Okay, so I'm going to play it and let it run, get down to 8 volts, 8-ish. Okay, so now I get 7.79 for the voltage, 7.794, a time of 1.47. Okay, let's let it run again to 7 seconds. 7 volts. Okay, 6.889 at 2.73. I'm getting around, I got exactly, look at that, I got it right at 6. 6, and that's going to be 4.14. And you'll notice that it takes longer to decrease in voltage as the lower the voltage gets, right? Because the lower the voltage, the lower the current. And the lower the current, the lower the capacitor discharges. Okay, so let's see, now we're at 4.956. And a time of 6.09. Let's get this. So 1, 2, 3, 4, 5. That's 5. I'm going to get one more term. You should get 10, okay? But I'm not going to do 10 because I don't want to. Okay, so 3.952, and this is going to be a time of 8.4 seconds. Okay, so let's now see how we would graph this. So I'm going to switch over here. We're going to make an actual graph. It's going to be awesome. Okay, so here's my data, 9 volts at 0 seconds, and here's my times, and here's my voltages. And I can't graph this on graph paper very easily, right? So what I can do is go back to the natural log version. So let me write this as V as a function of time, which is my data, divided by V0 equals e to the negative t over RC. Still not easy to use. But now if I take the natural log of both sides, I get natural log of V over V0 equals, the natural log of this is just going to be negative 1 over RC times t. So now if I plot the natural log as a function of time, the slope should be this. Okay, but that means over here that I actually need V0 is equal to 9. I need to calculate natural log of V over V0. I need to calculate these. I should use a calculator. That'd be the coolest thing. Do I have a calculator? I had a calculator. I guess I could do, okay, I'm going to do it on, I really should use a calculator because that's what you would use, right? I lost my calculator. Okay, I'm going to do it on, we can do it on Google. There's a lot of different apps out there that can do this. So let's just say I'm going to do this one. Oh, this is easy, right? The natural log of 9 divided by 9 is just L. You can do, let's see, if you do ln of 1, if you just type that in the search, what does it do? It says 0. Okay, 0. Okay, now I'm going to do ln. I'm just using Google. ln of 7.794 divided by 9. And I get negative 0.144. Okay, now I'm going to do that one. I can just change that top thing up there. 6.889. 889. And this is why I didn't do 10 because it would take forever. 0.267. And that has no units, right? Because I did voltage over voltage. Now I'm at That's 6. Negative 0.405. Now I'm at 4.956. Negative 0.597. Last one, 3.952. And I get negative 8.2, not 8, negative 0.823. Okay. So now I want to graph this on the vertical axis, this on the horizontal axis. So I'm actually going to get my graph paper. And I think this is a great chance for you to practice making a graph on graph paper. If you can't make it on graph paper, then you shouldn't be doing it on a computer, because I think that if you really understand it, you can do it on graph paper. So this graph paper might be a little hard to see, but the key thing that we want to think about here is what scale do we want. So I want time on this way. I want to go from 0 to 8.4 seconds. So I'm just going to kind of guess here. I'm going to draw a line. I can count these squares, but I don't really... Actually, these squares are... No. It's really nice when you get the ones that are actually centimeter long squares, because then you can just measure things. Actually, are these in inches? Which I hate inches. No. Okay, let's just draw it then. So I'm just going to go from here. What if I did the time from, let's put 0 right here, and then want to get to I need 9 seconds. So let's do 5 squares. If I did 5 squares, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You can't even see that. Good thing I looked. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's going to be 1, 2, 3, 4, 5, 6 seconds. 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I know this is tedious, but I'm trying to show you this is actually what you do when you're making graph papers. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4. So that's 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's 8. That's 10. 9. 1, 2, 3, 4, 5. Okay. So I got enough. Now, the one thing I guessed, and I got lucky, right? Because if I ran out of room here, I'd be in trouble. If I only went half, not even to half of the graph, I could always double the size and make it bigger. Because you want this as big as possible, because it's going to be easier for you to draw stuff. Okay, so now for the voltage, I'm going from 0 to negative 0.8. So let's start with 0 up here. And you don't have to have 0, 0 as the origin. And I'm not going to, right? Okay, so I'm going to say I need to go to 0.9. So if I did 5, it might not work, right? Because if I did 5, let's see, it'd need to get to that. So that's 19 centimeters. Oh, it's just going to work. Barely. Okay, I'm going to do it anyway. Okay, so I'm going to put 0 right here. And then I'm going to count by 5s again. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is going to be negative 0.1, negative 0.2, 1, 2, 3, 4, 5, negative 0.3, 1, 2, 3, 4, 5, negative 0.4, 1, can you see this? Yeah. 1, 2, 3, 4, 5, negative 0.5. 1, 2, 3, 4, 5, negative 0.6. 1, 2, 3, 4, 5, negative 0.7. 1, 2, 3, 4, 5, negative 0.8. 1, 2, 3, 4, 5, negative 0.9. Okay, now we can start plotting our data points. So I'm going to take my first data point times 0. Oh, it's going to be 0, 0. So that's up here. Okay, the next one's going to be at a time of 1.47. So this is 1, and so 2, 4, 6, 8, right? 10. So this is 1.4 would be right here. So it's somewhere in between there. So I'm right there on that line. This is where it really helps to have a measuring stick. And then my voltage is going to be negative 0.14. Negative 0.1, 2, 3, 4. Now those are going to each be, so 2, 4, 6. Did I count more? 1, 2, 3, 4. It's off. 1, 2, 1, 2, 3, 4. Why did I do 4s? 1, 2, 1, 2, 3, 4. That one's 5. I just messed up this whole thing. Okay. I messed this up. So I'm going to switch over to, let's do this in Google. Let's do this in Google Docs. Would that be good? Okay, let's do this in Google Docs. Even though I said you should do this, I just said you should do this in graph paper. And then here I am not doing it in graph paper. So, yeah, that's me. That's all on me. So I'm going to go over here to switch to my computer. And let's do drive.google. And let's go to new sheet. And I tell you right now, I don't do perfectly with equations here, but I'm going to make my best. Okay, so I'm going to plot ln of v over v0. And this is just a label versus t. So now I just need to enter my data. So I have 0, 0. Then I have 1.47 and negative 0.144. And then I have 2.73. And that's going to be negative 0.0267. You know, the one nice thing about using a spreadsheet like this is that if I did enter the raw data, I could actually take the natural logs in here, and that's kind of cool. But I already wrote it down, so we're just going to do it the long way. 4.1, oh wait. I'm doing these backwards. This is t. That's fine. 4.14. So this is actually this. Not with a t. And then this is going to be t in seconds. Another one doesn't have units. Okay, 4.14 is negative 0.405. 6.09 is negative 0.597. And then 8.4 negative 0.823. Okay, now let's make a graph, which I always forget how to do this. I should save it. RC discharge. How about that? So insert chart. Now, I do not want a line chart. I want a XY scatter chart. Okay, but that is, look, there it is, that's done. That looks good. Okay, so now what I want to do is click on this and data chart area. Maybe it's over here, let's see. Customize, major ticks. I always forget how to do this. Series. trend line. There was a show label. Use equation. Done. Okay, there I go. So this says that it is a linear function, which that's really linear, right? I mean, it is from a computer, but it is pretty linear. And I have a slope of negative 0.098. So let's go back over here to the paper. I had this. ln of v over v0 equals negative 1 over rc times t. So this is like y equals mx plus b. That's a t. So that's my y. That's my x. So the slope would be this. So I had slope of negative 0.098. And that should be in units of 1 over seconds. And that's equal to negative 1 over RC. So I already said R is 100 ohms. So from that, I can solve for C. So RC is going to be 1 over 0.098. C is going to be 1 over 0.098 times 100 ohms. And so that's going to be equal to C is 1 over 9.8. Is that right? So if I put that in my calculator really quick, I can say 1 divided by 0.098 times 100. And I get 0.102 farads. So that's the capacitance. Let's go check. Let's switch back over to the computer. So now I'm going to go back to my simulator, and you can read the value of this. So I'll say charge, discharge, show value, 0.1 farads. I don't know if you can see that. It's 0.1 farads. So it all worked. Okay. Now, there's a whole bunch of other things that you can do. In particular, this is something that I did. I had significant. One of the things that's off is because my resistance is not 100 ohms. It's more than 100 ohms, right? Because that does not include the resistance in these wires over here, which it does have resistance in the wires. So I turned that on because I thought it'd be cool. You can also put in some other cool things, like to have a voltage chart and things like that. It's pretty fun. Now, there is one other thing I want to do, and I'm going to do it in another video, and that's to model this discharging capacitor with Python instead of doing integrating both sides. And I'll do that in another video, but I'll leave you here with your RC circuits and play with this app, even if you have to mess around to get Java working, because it's really great. Talk to you guys later.